So as the last of the Jonathans to finish out this day of Jonathans, I'm going to talk about some work in coding quantum information in spin J systems where J is larger than 1/2, which is something that the San Miguel Sheriff Department might call working with a large spin the size of a small spin, kind of in with the name, the theme of the workshop. So like Raj said, I'm now at Google Quantum AI. This is work that I started when I was at the University of Sherbrooke doing a postdoc. And the recent work has been done with Shiva, who's here at the University of New Mexico. Okay. So we've all been talking a lot about bosonic codes at this workshop. I'm going to talk about codes in spins that are similar to bosonic codes. And I want to motivate that from the perspective that I found really very thought-provoking, very inspiring from bosonic codes, in contrast to more traditional quantum error correction codes, which here I'm calling tensor-product codes. And here, the thing that's really interesting to me is that bosonic codes help us realize what physics we were paying attention to when we were building tensor-product codes. So on the left, you'll see that we were getting our large Hilbert space by creating a tensor product of many systems. And really the only physics we were assuming about our system was some kind of physics of locality. So we were interested in correcting low-way errors because we assumed our physical processes weren't gonna be acting really non-locally all at once. Now, if you take that idea to a bosonic system, you have another large Hilbert space. There's no tensor product structure in sight, but the harmonic oscillator gives you an infinite dimensional Hilbert space that you can use to encode your information. And here we don't have the physics of locality to work with, but the Weil-Heisenberg representation gives us the relevant kind of physics for what we're thinking about. And so we have errors that correspond to photon loss, dephasing, and kind of the low weight nature of errors in the tensor code kind of situation corresponds to these noise operations happening for short times with bosonic codes. Another really interesting thing is the correspondence between what kind of logical operations are easy to do on these codes. So in tensor product codes, we really like codes that have transversal gate sets. And so here I'm using my favorite example, which is the 7-qubit Steen code, which has all of the Cliffords transversally. So which just means that if I want to do like a Hadamard operation, I can just apply a physical Hadamard on each of my qubits. And that will affect a logical Hadamard on my code. Same thing with the S gate. If I want to do a logical C0 gate, I just need to do physical C0s between pairs of qubits in 2 different set of codes. And we have something similar in KP. But before I get to that, now, I'm still doing okay? Yeah. I want to highlight the most important thing on this slide, which is the colors that I'm using. Now, we've seen a lot of plots here where these positive peaks of the Wigner function are in red so far this week. But I'd like to argue that we should all be using blue because this allows us to use red for negative, which is, I feel, very intuitive. If your bank account is in the red, it's negative. And I was also told earlier this week that even when you appeal to the temperature analogy, if you have a black body, blue is a higher temperature than red. So I'd like everyone to think about it.
This harkens back to the first in-person BBQ where we discussed Wigner function colors for like every hour of our off time.
Yeah, it's very important.
Blue is quantum and quantum is
negative. We'll talk after. Okay, now that we've gotten the most important thing out of the way, we can talk about transversal gates in the GKP code. This has been mentioned several times already, but the notion of transversality now comes not from doing tensor product operations, but from doing Gaussian operations. These are kind of the easy things to do in a harmonic oscillator. And in the GKP code, it's really cool because these Gaussian operations let you do all of the Cliffords. So if I want to do an X gate that takes the 0 state to the 1 state, all I need to do is do a translation in position. If I want to do a Hadamard, which takes the 0 state to the plus state, all I need to do is a rotation by 90 degrees in phase space. If I want to do an S gate to take the plus state to the plus I state, I just need to do a shear in the phase space, which is really nice. Okay, so these codes are somehow like analogous to one another, not only in their error correction properties, but also in their easy logical operation properties. And now what I'm interested in doing is trying to take this analogy we've made between tensor-product codes and bosonic codes and extend that to new physics. And the new physics is the physics of angular momentum. So here we're going to have a large Hilbert space that's not a tensor product structure. It's also not a harmonic oscillator, but it's going to be some large representation of SU2, so some system of angular momentum. This could be a nuclear spin, or it could be the rotational degrees of freedom of something like a molecule. The colors here. Yeah, ask Victor. Yeah. Well, there's also less red things there, so it's also similar to kind of like GKP. There's less negative spikes. So
all atoms that Mathematica has in a package, and it has colors for certain atoms, and I just picked one that was big enough.
okay,
Picture. I don't know what that is. It's probably not even a real chemical.
some atomic species. Yeah. Not that I know of. Yeah. These are the good questions, though. I'm glad we did this. Wonderful. So because our Hilbert space is made up of this from these large angular momentum systems, the relevant structure on this Hilbert space comes from the representation of SU2 that we have on it. And so in particular, the kind of errors you might be interested in correcting correspond to small rotations, which you can think of as the angular momentum operators. If you're because J plus and J minus corresponding to loss and excitation are linear combinations of these things. If you can correct small rotations, you can also correct loss and excitation, very similar to GKP. Now, there's many different ways you can think of putting quantum information in a spin system. I've just highlighted two here. One is if you have a really biased noise channel, maybe you're only suffering from dephasing, you might want to use something like a cat code. So there's several people working on things like this. If you're interested in working with the rotational degrees of freedom, you could do something like Victor's worked on with molecular codes. But the perspective that I'm going to come from is I want to think about encoding quantum information in such a way that I can do my logical operations using transversal gates. And what transversal gates means in a spin system is unitaries generated by linear Hamiltonians here in the angular momentum operators. And so this approach is very similar to what Arlie was talking about earlier this afternoon, her talk in oscillators. So for the rest of this talk, or for most of the rest of this talk, I'm just going to focus on trying to implement Clifford operations with these transversal unitaries. And so what that means is that I want to find some code space in my spin system such that I can do a logical escape by doing a physical escape on my system. So a physical quarter turn about the z-axis. And similarly, I would like to be able to have a code space where I can do a logical Hadamard by doing a physical turn of 1/2 about this x plus z direction on my actual spin. So if you think about this for a while, what you're really asking from like a group perspective is you're looking for a faithful two-dimensional irrep of the Clifford group within this larger irrep of SU2. Now the Clifford group has 8 irreps, and before I just focus in on the particular 2 irreps that I'm interested in, I thought it would be fun to walk you through what these irreps are to make it a little bit less mysterious. Also, I get a chance to show more pictures, and it's the last talk of the day, so you probably want to see more pictures than equations. So the nice thing about these irreps of the Clifford group is that most of them come very straightforwardly just from irreps of SU2. So of course, there's the trivial irrep Clifford group, which corresponds just to the trivial irrep of SU2 in spin 0, just a one-dimensional system. The spin 1/2 SU2 irrep corresponds to the ordinary irrep that we think about when we think about the Clifford group as 2x2 complex matrices. And if you go up to spin 1, you get an orthogonal array of the Clifford group, which orthogonal here just means that I can write all my matrices. And so this is just the symmetries. Can you still hear me? This is just the symmetries of an octahedron in R3. And then in spin 3 halves, we have a 4-dimensional array of SU2, and the Clifford group is also remains a 4-dimensional array in spin 3 halves. Maybe there's no nice pictorial way to think about that, but it's exactly the same picture you have from SU2. Once you get up to larger arrays of SU2, the fact that the Clifford group is only a subset of your SU2 rotations means that your full SU2 array starts breaking down into smaller arrays of the Clifford group. And so you find in spin 2 that you have another 3-dimensional array of the Clifford group. This is just like the original 3-dimensional array that we had before, except if you look closely at these matrices, you'll notice they're determinant -1. So they're not only like rotational symmetries of the octahedron, but they have extra reflections in there as well, which is kind of fun. And then there's this 2-dimensional orthogonal array, which if you think about it is acting on a qubit. This is a set of operations that are the symmetries of a triangle inscribed in one of the great circles of the block sphere. And the cool thing about this array is that if you try and encode your quantum information in this 2-dimensional space, it gives you an error detecting code for free, which is kind of fun. And then finally, in spin 5 halves, you have this other 2-dimensional faithful array of the Clifford group, which, similar to that kind of variant of the 3-dimensional representation, has some extra minus signs. So S and H act kind of like -S and -H, which doesn't matter when it's working on its own because we only care about the projective action of these things. But when your SU2 array starts breaking down into different copies of these arrays, you find that you have to keep track of these phases if you ever create coherent superpositions of them. Yeah, so the rest of spin 5 halves is the 4-dimensional array that we've seen before. Now, if you were paying attention, you'll notice that I said there were 8 arrays of the Clifford group, and I've only shown 7 of them so far. If you were really paying attention, and you know that there are 48 elements in the binary octahedral group, you would know that the remaining array is a 1-dimensional array. It shows up in spin 3. I don't have a slide for it, but it just puts some minus signs on the space sometimes. Like I think S and H probably are just multiplication by -1. So that gives us all of the ways that my large spin decomposes into different arrays of the Clifford group, what I want to have logical operations do. And because I want my physical Clifford operations to do logical Cliffords, I'm looking for just the 2 faithful 2-dimensional arrays of the Clifford group. These only show up in the half-integer spins. So I've listed for the smallest half-integer spins how many times you get each of these arrays showing up. And you'll find that the only array of SU2 that doesn't have either of these Clifford subspaces is spin 3 halves. Otherwise, you have things available to you all the time. So we found a place where we can do logical operations. The next question is, when can we actually correct errors, which is ostensibly why we're going through this whole exercise in the first place. And to do that, typical thing to do is check your nil-Flam conditions. There's a bunch because I have 4 different error operators, but thankfully, they're already built into my code spaces. You can condense them all down into these 3 conditions. And additionally, by realizing that there's some additional structure coming from the fact that I want my physical S gate to perform a logical S gate, you can look at the phases that the S gate puts on your angular momentum states and notice that this creates some restrictions on what kind of support your code words can have in the angular momentum basis. And you work things out, you'll find that this means all of my conditions reduce down just to a single condition that I need the JZ operator to have vanishing expectation value on the code words. So that's nice. This is something that's very, very simple to check once you have some candidate code spaces. So we can in fact just check that for all of these code spaces that we were identifying. And we find that the small ones don't work. They don't have vanishing JZ expectation values, so they won't allow us to correct errors. But if we bump ourselves up to spin 13.5 or higher, we start seeing that we have these code words or these code spaces appearing with multiplicity, which allows you to like engineer your code words a little bit. And you can take advantage of this extra degree of freedom to create a code word that makes this expectation value vanish. And you can correct these angular momentum errors that we're looking to correct. Of course, spin 13.5 is kind of large from a nuclear spin perspective. So if you expand your search a little bit and don't look specifically for Clifford irreps, but you look for another discrete subgroup of SU2, the icosahedral group, you find that you can find a code that allows you to correct all of the angular momentum errors in a spin 7/2. And so there's been some interesting recent work looking at this code, both from an experimental perspective and also from a more mathematical perspective. So it turns out there's lots of really cool things about this code. I'm not going to talk more about it now, but you can ask me afterwards if you like icosahedra. So now we get to, this was kind of previous work that I've been discussing so far. Now we get to the recent stuff that Shiva's been doing with me, which is very much in the spirit of a lot of the bosonic code talks so far this week, which is I want to look at a genuine multi-spin error correcting code. So I don't just have a single large J spin, but I'm going to have several of them. And so I want to incorporate like both the tensor product structure of the fact that I've got several spins, but also take advantage of the large Hilbert space of each of my individual spins. And you could do this, of course, by concatenating, and people look at that. But we want to look at this from a more like intrinsic level, with it is not merely concatenating one of our codes with a traditional tensor product code. Good. So here, of course, the idea of transversal is now going to be a combination of doing those SU2 rotations, but now in parallel on multiple large spins. Now, the really important thing for these codes is that, unlike the case of spin 1/2, which I think we're all kind of raised on, the totally symmetric subspace of a collection of large J spins does not turn out to be a single irrep of SU2, but it in fact decomposes into many irreps of SU2, which you can count using these like Young diagram kind of things. If you want to find out the degeneracy of the JZ operator in these symmetric subspaces. And this is nice because having this direct sum of different SU2 representations or irreps allows you to do some of this code engineering I was talking about earlier. And so just like, unlike before, where I had to go up to spin 13/2 in order to get a Clifford code that allowed me to correct my random rotation errors, now just with a collection of 3 spin 5/2, I can engineer myself a code using the spin 11/2 and 9/2 irreps that lets me correct small random rotation errors. And in fact, again, if I kind of expand my search and I allow myself to look for codes that just have binary tetrahedral operations, then I can even go down to lower spin and do 3 spin 3/2 systems, which is a Hilbert space the same size as a 6-dimensional qubit code. So it's really close to kind of like the lower limit that we have with a 5-qubit error correcting code. Now, in addition to being able to work with some smaller spins, thanks, Rush, we can also correct higher order errors. So for correcting first order errors, I showed that there was only a single condition you had to check for the Canilla-Flom. For second order errors, you end up getting some more. It's still drastically reduced from what the full set of all of these second order errors could be. But you do have to do a little bit more work in this case. Shiva has done this little bit of more work and found that you can, in fact, come up with a code that corrects second order errors in angular momentum with just 3 spin 7/2 system, which is very nice. Not only does the second order angular momentum errors kind of correspond to maybe larger rotations, SU2 rotations, but also additional air channels that you get from optical pumping, other relevant noise sources in these kinds of systems. Good. So now for the last bit, I want to kind of return to purely tensor product codes. So we started by moving away and kind of generalizing principles from tensor product codes to give us these spin codes. But now we have these spin codes in large J spins, and I can think about actually implementing them as a tensor product of many qubits, because the totally symmetric subspace of all these qubits is going to be a large J spin. Now, the first thing that you might ask yourself is, well, I designed my codes to correct against global SU2 rotations on all these spins. So is this actually going to correct for anything relevant to my tensor product structure when I build this out of a bunch of qubits? And it turns out that, in fact, they do when you build these codes in the totally symmetric subspace. So for distance 3 codes and distance 5 codes, you can make them make distance 3 and distance 5 qubit codes just by building a large J code that corrects first or second order angular momentum, global angular momentum errors, which is very cool. In particular, you can use this to build yourself a distance 5 code with 25 qubits, which kind of pleasantly corresponds to the surface code, distance 5 surface code. Of course, you're making trade-offs here. You can do all of your Cliffords transversely, which you can't do in the surface code, but you've lost the stabilizer structure, which is one of the main reasons people like the surface code. So, with that, I think that brings me to my summary slide. So yeah, I hope I at least got you a little bit excited about thinking about porting all of these lessons we've been learning from bosonic codes into additional physical systems. Really taking to heart this message that we should be correcting physically relevant air channels and taking advantage of the symmetries of our system. Yeah, like seeing that looking at these codes gives you a fresh perspective on qubit codes as well. So with that, hopefully I didn't go over time. Okay.
We have plenty of time for questions.
Simple and naive question. All of the codes that you construct, are they by construct stabilizer codes?
Yeah, there's no stabilizers in sight.
Can you construct stabilizers?
I mean, it depends on how broadly you want to think about a stabilizer. You can construct operators that
and
stabilize.
Pauli's, you can take the Pauli's to the power of.
Yeah, you have to go high order in angular momentum operators to build these stabilizers.
And you have a procedure to always determine if stabilizer group exists.
Stabilizer group. Yeah, I don't think you can get the like commuting group structure within SU2. It's just like too non-commutative a group.
Okay, thanks.
Is it just not a abelian stabilizer group?
Yeah.
You just express it in terms of spin coherent states.
Yeah.
And then it's like a spherical code. You have a polytope with points in the spin coherent states.
Yeah, if you're happy with non-abelian, sorry. Yeah.
Yeah, this all boils down to this general problem of decoding non-abelian stabilizer
Yeah,
codes. Just like, I don't know how to do it.
So
Yeah, you can measure the
when
errors.
you're dealing with a collection of spin 1/2s, right, and you've got your collective spin, how does the protection work when you start having higher temperatures? In that, if you start considering temperatures, degeneracies start to become a large problem, right?
Higher temperature. Well, so when you say higher temperature, my mind goes to thinking about like excitation errors, kind of like incoherent excitation of the spins.
Sure.
And if that is the primary noise channel you have in this setting, correcting the local rotations allows you to correct excitation errors, provided they're not too strong.
But okay, yes. And how does the degeneracies tend to scale when you start with, say, spin 13/2, like a collection of 4 of those?
Oh, I wouldn't know off the top
Okay,
of my
so
head.
you just have to go through the Young tableaus in a higher dimensional case?
Oh, that kind of degeneracy.
Yes, sorry, that degeneracy.
How did the degeneracy scale? They scale the number of like air reps you have of the different kinds. It scales linearly with the dimension of the Hilbert space asymptotically.
So the degeneracies or the set of values you have?
Like the number of copies of a particular air rep.
Okay.
Yeah, it scales linearly.
Thank you.
There any more questions? And let's thank